Now, we just talked about the third law of thermodynamics, which says that the entropy of basically all systems is greater than zero. Only time you can have zero is for those perfect crystals, which is like never. But we kind of skipped over the second law. And in order to talk about the second law, we need to do a little bit more flashback from Chem 222 about things with enthalpy. So in Chem 222, this is just a review, if you're going to heat up a substance, but it's going to keep the same phase, i.e. you're heating up a liquid, but you're not turning it into a gas, or you're not turning your solid into a liquid, etc., you can use Q equals mc delta T. And we talked about how C was the heat capacity, 4.184 grams for joules per gram Kelvin for liquid water. Delta T, final temperature minus initial temperature. M is the mass, stuff like that. But if you do change the phase, then you have the mass times the heat of something. And this can be the mass in grams or moles. The heat of something will be some kind of phase change, like a delta H of vaporization. Those are all things that I would give to you. And those are things that you can calculate. I will give you all the values you need except for the liquid heat capacity, which is 4.184. I want you to know that number. That's going to come in really handy, and we do so much with water. You've got to know 4.184. But all the rest of these things I would provide you. So in Chem 222, we figured out the energy change of, for example, taking ice down the lower left-hand corner and melting it to liquid water, and then heating the liquid water, and finally turning the liquid water into a gas through evaporation. And we talked about Q equals mc delta T, and we talked about the heat times the delta H's of the different values. But again, these are all things that would be given to you, but if you don't remember this, it might be a cool idea to go back and check that chapter out. In Chem 222, we also figured out the delta H's of the different reactions. It usually came from the summation of the delta H of all the products minus the summation of all the delta H of reactants. That little sigma right there just means add up all of them. So you add up all of the entropies of the products and you subtract the entropy of all the reactants. And you'll use that table from we talked about earlier to find the different delta H values. You don't have to know any of those. So for example, if you wanted to find the delta H for two hydrogens and oxygen making liquid water, you would look up the respective values. And again, it's products minus reactants. So you'd have liquid water, which is minus 285.85, and you can look this up. I wouldn't know what it was off the top of my head. Multiply it by 2, though, because each of them in the table is per mole, and there are 2 moles of water. Then you subtract the 2 moles of hydrogen and the 1 mole of oxygen. The elements in their pure states have values of 0 when you look them up, or you can just know it. Delta H for this reaction minus 571.70 kilojoules per mole. So this is again an overview of how this process works. The delta H we calculated was exothermic. It's a negative number, so energy is released. If it would have been a positive, say 571.70, that would have been endothermic, and it would mean that you'd have to add energy to make it happen. And finally, that little degree symbol right there, the little 0 superscript, whatever, that means standard conditions. So 298 Kelvin, an atmosphere of pressure, 1 mole per liter, stuff like that. This is a review of Chem 222. And again, if some of this is looking a little foreign, reach out to me and I'll share with you some of the resources from Chem 222 just to get you back up to speed here. So when you want to find the delta S of the reaction, and that would be the entropy change for the reaction, it's going to be really similar to what we did with delta H just a second ago. You're going to take the sum of all the entropies of the products minus the sum of all the entropies of the reactants. And you'll use that table, that mhchem.org/thermo, or the one at the end of problem set 1 of Chemistry 223, in order to look the values up. So for the same reaction we just looked at for delta H, let's figure out delta S of this reaction. So it'll be 2 liquid water molecule entropy minus the reactants, minus 2H2 and an O2. Now the difference between entropy and enthalpy is that the only time you're going to have 0 entropies will be for the pure crystals of elements at 0 Kelvin, and we are not at 0 Kelvin, that's for sure. So all the values that you look up will be positive numbers. So notice there that the liquid water has a value of 69.9 93.9 when you look it up, and you'll multiply that by 2 because it's per mole. Then you'll subtract the 2 moles of the H2. H2 is 130.7 joules per mole Kelvin, and also the 1 mole of the O2, which is 205.3 joules per mole. So at the end of the day, you end up with a delta S for this reaction minus 326.9 joules per Kelvin. If delta S is negative, that means that entropy is not increasing. Entropy is actually decreasing as you go from reactants to products. You're going from 3 moles of gas to 2 moles of liquid. The gases always have higher entropy than liquids, so that's one reason why it's going down. And also you're going from 3 moles of reactant to 2 moles of product. And in the entropy world, that's kind of like making your matter more concentrated. Entropy would like it if you have more moles on the product side than the reactant side. But here we're going from 2 plus 1, 3 moles of reactant to 2 moles of product. That's kind of like cleaning your room, all right? So entropy is not very happy here. It's giving us a negative value, and that'll have some implications for what's going on. So here's a reaction. Copper metal is reacting with oxygen, O2, to make copper 2 oxide, CuO. And the question is, what's the entropy change, the delta S of the system, for this reaction? So what you would do is you would take the entropy of the product, the CuO, and you would subtract the copper entropy and 1/2 times the oxygen entropy. And there are the different values. You don't have to know those or anything like that. Well, if you do this, then it comes out to be minus 93.12 joules per Kelvin. Pretty simple, plug and chug kind of stuff. Again, you don't have to know any of the entropy values. Remember, the raw entropy values will always be positive numbers unless you happen to be at 0 Kelvin, which is never. But delta S may or may not be positive or negative. And in this case, as you can see, delta S, the change in entropy, is certainly a negative number. In Chemistry 222, we talked about the enthalpy of formation, or the heat of formation. And when you have a formation, delta H, you have that little symbol there, the little subscript F, which means formation. And in terms of enthalpy, delta H, that means you have 1 mole of product, and all the reactants have to be elements in their standard states. Well, there's an equivalent in entropy. There's what they call the entropy of formation, delta SF, or formation entropy. And likewise with delta S, you want to have just 1 mole of product, and all reactants are elements in their standard state. So in this example, we're calculating the entropy of formation for hydrogen plus oxygen making liquid water. And again, because it's a formation, we have to have 1 mole of product. We can't have a 2 right there. So in Chem 222, I was whining about how, oh, even I have to use fractions here. I have to use fractions here as well, because you can only have 1 mole of product, and oxygen always comes as a diatomic, so we're stuck with the 1/2 O2. But anyway, delta SF would be products minus reactants. You can look up those respective values. So liquid water, 69.9 joules per mole Kelvin, and then you subtract the H2 and 1/2 the O2, and you end up with minus 163.5 joules per Kelvin. So if you have to calculate a formation entropy like this, no problem. 1 mole of product, reactants in their standard states, good to go. So here's a question. Which of these reactions is an entropy of formation? Delta SF, all right? And again, to have a delta SF, you must have 1 mole of product, and all reactants will be elements in their standard states. So if you look at this just a little bit, you can see that B is not going to work because you don't have 1 mole of product. You have K solid, 1/2 Cl2, 3/2 O2. You don't have just 1 mole of product, so that's out. Now in C, you do have 1 mole of product, it's true. However, the reactants here are not elements in their standard states. Calcium oxide is a combination of calcium and oxygen, so it's a compound. And carbon dioxide, same thing, combination of carbon and oxygen. So that one's flat out. Reactants are not elements in their standard states, all right? I missed A, I should go back to that. A doesn't have elements in their standard state. It has hydroxide, a polyatomic ion, and manganese 2+, those aren't the normal ways that any of these would form, so that's not going to happen. I guess let's go to E, what the heck, since I'm getting all over the place here. We don't have 1 mole of product, all right? You've got 8 moles of H2S, and that certainly is more than 1 mole, so for that reason, that's disqualified. However, you can probably imagine if you look at answer D, you are good to go because you have 1 mole of product, NaOH, and all the reactants are elements in their standard states. So oxygen and hydrogen are both gas, and sodium is a solid. We're using weird fractions here, which even I have to do because you're stuck with 1 mole of product. So D here would be an entropy of formation equation.